Jean-François, I don't hear you.
You don't hear me? Can you hear me?
Now it's good.
Okay, all right. Yeah. So I was just saying, hello, Jean-Marie. Nice to see you. And introducing the plenary lecture, I was saying also hello to the person online, because some person are also following your talk on Zoom and maybe also on YouTube. So you have other person, and all you can see the room. You have all the attendees of the conference here in India. So it's a real pleasure to have Jean-Marie as a plenary speaker. So I will not make a very long introduction. So Jean-Marie, as you may all know, is the father of the field of supramolecular chemistry. He got the Nobel Prize of Chemistry for this in 1987. But actually, he also developed many other domains and topics. For example, the chemistry of complex systems, also working lately a lot on cancer research with some molecules in clinical trial. And today, I think the talk would be more about dynamic materials and dynamic chemistry applied to adaptive materials. So I will remind before you start, Jean-Marie, that as this is an online session, there will be no questions. So we will just close after the session. And with that said, Jean-Marie, this is your stage, and we are looking forward for your talk.
Thank you very much. You know, it would be nicer to be there, of course, as usual, but Zoom makes things possible which otherwise one would be unable to do. So I want to thank the organizers of this meeting for this occasion to talk to them and to present some of our work. The title is Macro, in parentheses, Molecular Assembly and Materials. So that I like that very much, because I'm not really a macromolecular chemist, like for instance Jean-François is and many in the room. But I have some macromolecular results, and much of it is also molecular assembly. So the title of my lecture has to do with dynamic materials, dynamic polymers, dynamers, and dynamic materials. And then we will have different types of different types of systems which I want to describe. Some are already quite well known, but the end of it is very new. So you will see. Okay, so first of all, let's start with the basics. Supramolecular chemistry is based on labile non-covalent interactions, which means it's a dynamic chemistry. What does that mean? It means that the constitution of the supramolecular objects can modify themselves by component exchange due to the fact that the bonding between the entities are rather labile. So this is a dynamic non-covalent chemistry, which one can then try to transfer into molecular chemistry, which is usually the domain of strong covalent bonds. But there are in chemistry, in organic chemistry, a number of bonds which are chemically reversible. And therefore, these dynamics can be imported into molecular chemistry. And that's a dynamic covalent chemistry. So I thought that it would be good to have just one type of description, the name of the field of dynamic chemistry, both on the non-covalent and the covalent level. And the name which I like to use is constitutional dynamic chemistry, meaning that it is a chemistry which is dynamic both on the supramolecular and on the molecular level, covalent and non-covalent. And of course, the result of all that is that because the components of these objects can be exchanged, they can adapt if the conditions change due to a physical stimulus or a chemical effector. And this goes towards what we like to call, what we are now mostly doing, adaptive chemistry. Now, these and adaptive materials, of course, also, which is an important consequence of adaptive chemistry. So these constitutional dynamic materials then are based on reversible interactions, and especially, of course, on the level of non-covalent. It's obvious because there are labile non-covalent interactions, and on the level of covalent entities, there must be reversible covalent reactions. So we have two features, two areas. One is a polycondensation based on reversible covalent reaction, which means that it's a molecular covalent dinamers, dynamic polymers, which are molecular and which are dynamic because the bonds, the connections are reversible. So if you have here a monomer with two functional groups in yellow, another monomer with two functional groups in red, they can undergo a condensation between the red and the yellow, leading to a polymer, to a dynamic polymer, which is this polymer is of covalent type. The bonds between the yellow piece and the red piece are reversible covalent connections, covalent bonds. Now, on the other hand, if the interactions are between recognition groups, the yellow is a recognition group and the red is a complementary, both are complementary recognition groups linked together by reversible non-covalent reactions, interactions, I should say. Okay, I have to be clear here. On the covalent level, it's a reaction. On the non-covalent, it's a physical interaction. So there's quite in terms of the basics, it is quite different in as much as molecular covalent dynamers are based on chemical reversible reactions, and the non-covalent dynamers are based on complementary recognition type physical interactions. So let me first have a look at the supramolecular polymer chemistry, because it's the one which did not exist some time ago, 20 years ago, 30 years ago now, and just to tell you. So supramolecular polymer chemistry, first of all, if you want to make main chain polymers, and this is something we did a long time ago in 1990, but I needed also for one application. That was based at that time in a paper in 1990 on a reaction on recognition groups, which are here pyridine with amides. So this means that they have an interaction group, which is a donor of hydrogen bonding, an acceptor and a donor. The complement to that is another monomer where the functional groups are accepting hydrogen bonds or donating or accepting. Now, the spacer between that, this is this entity which has two end groups which have recognition groups, and in the center there is a spacer. I will not insist on the spacer right now. Let's just say that it's a spacer derived from tartaric acid, where the OHs of tartaric acid are functionalized by C12H25 units, as to make them well soluble, and there's another property you will see. And so, if you now look at these two complementary monomers, complementary in terms of molecular recognition, if you mix them, you get a main chain supramolecular polymer, where the binding between the units is due to physical complementary interactions of recognition type, as you see here. This means that there are three hydrogen bonds formed between the end groups of these monomeric entities. Just to tell you something quite of interest, but it's now old, of course. This is a solid on the left. This is a solid on the right. They have melting points. And when you mix them, you get a liquid crystal, which is liquid crystalline in a very extended domain up to over 100 degrees. So this was then very much applied, very much studied. We did some, and of course, Bert Meyer in Eindhoven did a very important contribution to it. And this is the kind of things you get, the kinds of fibers, so to say, you get, which you can here see by electron microscopy. And but you can call this an emerging property, the fact that from solid, you go to liquid crystals. Now, there are three levels of this assembly. That is also something quite interesting, which is that, first of all, you have these molecular components, which undergo then interaction through recognition groups to lead to a supramolecular polymer chain, but that is not finished. So if you look in more details, you can see that by looking at the X-ray scattering data, which were done in Orsay. And we can find out, and this was found out, that there's a triple helical strand where 3 of such supramolecular polymer chains wrap around an axis of a cylinder. And what is sticking out of the cylinder, that is long C12H25 chains, which are important in terms of the material. So the core is a cylinder with a triple helix, triple helical strand in the middle, as this in the center, and sticking out are the C12H25 chains you see here. And this can then be measured as 15 degrees diameter in the center and about 40 degrees for the total thing. So, and then what happens is that because these chains can entangle, you get lateral associations in triple helical strands by electron microscopy. And you see here 2 strands which connect with each other and make a larger helical strand. And all these things are helical. We have studied that much more, but it was a long time ago. So this is a sort of a self-organization starting on nanoscale, the components, the initial ones, going to microscale because these fibers, they have micrometer dimensions. We can also speak of another type of supramolecular polymers, which are of columnar type, which is the following. If you have a flat molecules, components, which can interact through hydrogen bonding, forming this kind of a disc-like entity here. This is a sort of a discotic liquid crystal, and then this can pile up and lead to a columnar supramolecular polymer. Another type is the one which was much studied in Eindhoven also, but by the group at that time, but it was the group of David Reinhardt, and David Reinhardt, he studied this in 20, and this rosette is now as hexamer, not a tracer. The first thing I showed you was a trimer. This is now a hexamer, and they can pile up also. And there was a lot of very nice chemistry done by the group of David Reinhardt in 20. This is the principle. You have a sector which can assemble into a disk. Like here is a trimeric disk, here is a hexameric disk, and then they pile up to lead to a supramolecular polymer of columnar type. This has some importance for later on, as you will see. So the self-organization is first the sector gives a supramolecular disk, and the second step of self-organization is the disks pile up to make a supramolecular multi-layer column. One can also make interesting things. We have made quite a few of these supramolecular polymer entities and films. When we take this type of entity here, where we have here an isocyanate and here a hydrazide, CONH-NH2. So one monomer here has CONH-NH2 groups, one on each end, and the other one is a single. It has also these 2 isocyanates group, so they can condense to give this polymer, as you can see here. I don't insist on the physical properties, you see that there. And what is interesting, there's a very high density of hydrogen bonding sites in several functional groups, which I will now look at. First of all, here you have a bis acyl hydrazine. This is a bis acyl hydrazine. And then you can identify in this a urea group, which is known to be nicely forming hydrogen bonds, and a urethane over there. So all this together gives a lot of hydrogen bonding interactions to this polymeric entity. And it has also interesting property material. This was studied by one of my Indian co-workers, a postdoc, who is now working at BASF, Nabarun Roy, who is now working in Germany with BASF. And this gives a very interesting material you see here. It gives a transparent film. This one, we have other things, but I won't just illustrate it this way. This film was made by Nabarun. Here are his fingers. These are the 2 hands of Nabarun. And here's somebody else, of course, is cleaving the film. You know, it's a very nice film, very transparent, nicely transparent. It doesn't lead to any deformation of what goes through the film. The film gives no deformation. So it's cleaved with scissors. and you cut, and then this transparent film, these pieces now are superimposed. You press with your finger at that point, and after waiting for about a few minutes, you can now have you get this film, you can pull it now, you can stretch it, and it sticks. So that's a very interesting case of a sort of a self-healing material based on supramolecular polymers on non-covalent interactions. I don't want to get into that. These are just physical data. Now, one thing which then came out of this, sort of unexpectedly, but of course you can always expect it, but we didn't dream of it, so to say. A group in Eindhoven made biomaterials out of it. And our first paper was in 1990, as you see here. And it happens that then they made biomaterials, which are biocompatible polymers. And in 2013, I got this email from this small company, Xeltis, which is now bigger, of course. They developed this supramolecular polymer films for application as cardiovascular implants for children. So surgical treatment of children having a severe cardiac malformation. And this was then done in 2013, 23 years later, and this is the first case. This is a young girl in Russia, in Moscow, 4-year-old Dominika in 2013. And professor here, Leo Bukharia, was the surgeon who did the implantation on October 23, 2013 at the Bakulev Scientific Center for Cardiovascular Surgery. They are both very happy, and we were very happy, of course, to see that one of our things, which were totally basic research, ended up in the body of children. And it took 23 years, but that's easy to understand. But because if you want to do something with a human being, you have a lot of steps to go to get accepted and so on. But it worked, and now many more than 10 children were treated, and the company also developed heart valves. The heart valves are a bit more difficult to operate because they move, and so it's more complicated. So they have also now made tubings to implant and to replace, for instance, in vascular surgery to have replacements. Okay. Now they tell me that's a breakthrough in surgical practice. Of course, I'm very happy about that. So now, if we want to go now from the supramolecular level to the molecular dynamic covalent chemistry, we have to look for reversible reactions. One simple one is the condensation of an amine with a carbonyl to give an imine and the formation of water. And this is a reversible reaction, which is very well known since Hugo Schiff many years ago, more than 100, let's say about 150 years ago. And then one can also have another process where the LH2 can react with the imine to form react with the imine to form an aminal, and then can exchange also. So dynamic covalent carbonyl condensations can lead to different exchange processes. One is simply forming the imine and then dissociating again and forming again, just forming dissociation with water reacting as nucleophile, or an amine reacting with the imine, forming here then an aminal, which can go also back and forth. There's another reaction I want to insist on because I need it really at the end of my talk. This is something which was found by one of my students, of my PhD students, Seridan Kulchat, a lady from Bangkok, from the University of Khon Kaen in Bangkok. And this was quite an interesting one. Of course, it's much less well known, but it is very interesting in terms of its mechanism. This is a Knoevenagel compound, which is a condensation of a barbituric acid with an aldehyde here, having this double bond. This double bond is very electron poor because this is a very strong electron attracting piece, the barbituric unit. So if you treat it with an imine, you see here, that's an imine. This nitrogen of the imine can react with this carbon of our Knoevenagel, forming a four-membered ring, an acetidine intermediate. This is a four-membered ring and is reminiscent of metastasis which is the basic of metathesis using organometallic type of reactions. Here is purely organic, and now when you get this intermediate, which was then studied by one of my Chinese co-workers, Dr. Wei Gu, this can now split either by 2,4, which just goes back, that's a silent process, you don't see it, or by 1,3, and then you get exchange of the components, the red and the blue exchange. This is quite an interesting reaction because it is very fast. Whereas these reactions here are slower, this one is very fast, almost immediate. So let me see, I'll show you later why I need it. Okay, so what can we do with these covalent dynamers? Some interesting thing is that together with some co-workers coming, which have been sent to my lab by Mitsui Chemicals in Japan, we can make materials green, what I may call nowadays, it's always nice when it is green, water disintegrative green plastics. It is doubly degradative because it has a piece which is degraded, it can be degraded by reactions, and another one, an imine bond, which can be degraded by chemical degradation. So the centerpiece is a biodegradable entity, and then in water, the imine bonds are degraded so that the big polymer, so to say, gives small pieces, which can then be nicely degraded by biodegradation. So there are two types of degradation, double degradation. One is by simple hydrolysis, and then there is one by biodegradation by microorganisms. So here is the example. One can make a polyimine by taking a bis-carbonyl, bisaldehyde, reacting with a diamine, giving a polyimine. And this then gives very nice materials. This has been developed by Mitsui Chemicals. As you can see, that's quite a nice material. They made 300 kilos of that thing because they wanted to sell it to different personal care companies, for instance, to make diapers for children, for babies, and so on. The trouble is it's still a bit too expensive compared to classical type of plastics. But I'm convinced that at some stage, if we have to go away from plastics which are not degradable, this kind of film will be very interesting because it can degrade first in water and then it can be degraded by microorganisms. The imine bond is cleaved by water, and the other one, the other piece in the middle, is biodegradable. Now let's look at one, this double disintegration. As you see here, so we have a biodegradable polymer, and this is fitted with imine bonds at a given distance, depending on this piece in the middle has a molecular weight of 6,300, and here of 2,500 only. So here there is no imine. Here there are imines, and here's a higher density of imines. And you see, if you take one of those films, you put it in water, at this one, after 6 hours, has no change, no degradation. This one, where the imines have been introduced, so it can be hydrolyzed, is slightly disintegrated after 6 hours, whereas this one is much more and almost completely disintegrated. You may note also that if you don't let it disintegrate too long, if you take it out, if it dries, if it becomes dry, it will reform. So one can also, it's somewhat reversible, and the disintegration rate can be controlled by the proportion of imine bonds, which makes it adaptable to different types of users. Now, they have another property, these dynamic covalent dynamers, which is the following. Suppose you make a film where you have a bis-carbonyl and a diamine here, and then you get a polyimine AB. Now you take another bis-carbonyl, another diamine, you get now A prime, B prime, A prime, B prime. You take these two films independently generated and you put them on top of each other. If, as we expect, as we have by construction obtained because they're imines, this connection is of course dynamic. And in each film, the connection is dynamic. So it can separate and can recombine in a different way, shown here. If this bond breaks, and if this bond breaks, you get another combination, because when you have an A-B in one film and A'-B' in the other film, there are two combinations which are still possible. A can combine with B', as shown here, through the interface of the films, and A' can combine with B. So you have 4 combinations possible. You start with 2 because you prepare them separately, you superimpose them, and you let it go. So this were done in meantimes. So what you can first, of course, make dynamic polymer blends, but very interestingly also, you can see the following. Optical properties are interesting because you can see it. And as people say, seeing is believing. So I show you an example of optical dynamics, optodynamics. These are optical changes of dynamic polymers due to bond recombinations, the one in the way I've just shown you. So you start with the film AB and the film A by A', B'. And these connections, as we have seen, are reversible. And now you superimpose here by a corner. At this place where they are superimposed, they can generate 2 new combinations, A with B' and B with A'. So that if there is a color, if one of these new combinations has a color, or if one of these new combinations has a fluorescence, it will, of course, show up. You will see it. A', or A', may have a color, may have a fluorescence, which were not present at the beginning. And so my Japanese co-workers, they made that little picture of the head of a cat, where the head and the ears is polymer AB, the whiskers, the mustache, the eyes and the inside of the ears are polymer A', B', and now they are superimposed, and they can now undergo this exchange. And we knew, of course, we had prepared all these polymers separately, and you can see a yellow color appears where they superimposed, or a fluorescence, a green, yellow-green fluorescence appears where they were superimposed. That's, of course, a proof that it works, that the recombination occurs at the interface of the films. It also shows that you, in principle, could write with a heating laser at the interface between the two, and you could also do that on a stack. If you stack these films on top of each other, then you can write in 3 dimensions. I don't think it has been done, but it's certainly a possibility. Now, you can also make a lot of other things of this type, using always this combination of carbonyl and amine, taking this very simple compound, which is the urea with 2 amino groups. That means the carbonyl bis hydrazine, or diamino-urea, if you wish. It's another way of speaking. This gives bis imines of 1,3-diamino-urea. And this is also what is interesting is that there is a twist between on the NN bonds. They like to be not in plane but perpendicular, and so you get an orthogonal. That's an orthogonal dynamic subunit, which can make supramolecular non-covalent hydrogen bonds and molecular covalent imine functions, which means it's a doubly dynamic material. It is dynamic by the imines present, and it's on the covalent level, and it's dynamic by hydrogen bonding on the non-covalent level. So you can get this kind of polymers which are hydrogen bonded through this. Of course, I don't want to insist on it, but metals can be called supramolecular polymers, which are based on metal interactions, can be called metallo-supramolecular polymers. Let me just very quickly show that if this yellow unit is a binding site for a metal ion, then two of these monomers can be connected by the right metal ion, the red one here shown, and this can then lead to the connection. This can lead to metallo-supramolecular polymers, which can be then combined in different ways. One interesting one is that if you make the connections here, the connection is yellow with the red in the middle, if the yellow is a unit which can be ionized, like for instance, if this X here is H, then you can ionize it, you get an N minus, and that means that with a divalent metal cation, you get a neutral metallodynamo, which is quite interesting because you can use an organic ligand, a polar charged metal ion, they combine, they make this polymer, and at the same time, you can abstract the H because it's ionizable, and you end up with a neutral metallodynamic polymer. Okay, now let's go towards adaptive chemistry. As I told you, this is something we are very interested in these times. Okay, so adaptation can occur because it's dynamic. Adaptation can occur by response to different type of factors, physical or chemical, and lead to adaptive systems. Especially interesting is when this adaptation can drive supramolecular self-organization. I will show you that in a moment. This is at the end of my talk. I will be a bit, we'll have to, since the time is going along, I will drop a few of the slides. Now, the most quite impressive thing which we obtained is together with my colleague, the group of people of Paolo Sabori, who does nanochemistry. So, using this long chain aldehyde and 3 different diamines, C3, C6, and C12 diamine. In phenyloctane solution, you get a mixture of 3 monoimines, not even diamines. This is just very uninteresting. It just combines somewhat, it makes monoimines, and that's it. But then you take a drop of this solution in phenyloctane and you deposit it on graphite. If you deposit it on graphite and look at it by scanning tunneling microscopy, then you find that it is something very quite incredible has occurred. This mixture of 3 incomplete reactions, these 3 monoimines, leads to the deposition of only one single entity. The single entity is a bis imine only with C12, as you can see here. What does that mean? That is quite impressive because the simple adsorption has driven the reaction to completion and has driven also a selection of the components. You have now the bis imine and only the C12. And there's an adaptation due to the adsorption forces on the surface. And this is self-organization. The self-organization on the surface, this physical forces, adsorption, has driven selection also. Of course, we can also sort of think that at some stage in the origin of life, I don't claim that these compounds, of course, have anything to do with the origin of life, but one can say that the fact that simple adsorption on a surface can drive a reaction and select components indicates that it is a factor which may have contributed importantly the complexation and the complexification of matter. Now, let me drop that because this is would be too long. One can also make biodynamers. That means one can use different derivatives of biological monomers to lead to biopolymers. We have done all 3 of them. I want to just very quickly to show you. On one hand, making dynamic nucleic acids. It's not really nucleic acids, are analogs of nucleic acids, where the connections are dynamic. One can make dynamic peptoids, and so peptides which are dynamic, but can also make dynamic derivatives of sugars, of sugar pieces, of carbohydrates. All these 3, we have just done a little bit on it, and I think there is a lot to do here, especially I think with applications also in biology, because making dynamic peptoids and dynamic glycodynamers, these are adaptive, they can change depending on what happens, what are the conditions. they can change the constitution, and this would be still a domain, an area where a lot has to be done. And I would encourage everybody interested in biopolymers to try out and to sort of study these things. Now, let's look at complex systems, and we have to analyze them now. If these entities, constituents, can exchange pieces, in this mixture of exchanging things, there are relationships. What are these relationships? Let's start in the same way as I already said. Suppose we have components A prime, B, and B prime, which can react the A's with the B's, therefore forming, as I've already shown earlier, AB, AB prime, A prime B, and A prime B prime. This forms a network, and this is a dynamic network because the combinations, the A is combined with B through a reversible covalent bond. And what is this network? The simplest you can imagine, a square. This network is a square, and if you now look at the relationships between the constituents in this network, this square network, if you put the constituents at the corners of the square, and if you look at the edges, you see that AB shares A with A prime B prime, and AB shares B with A prime B. So AB shares A with AB prime and shares B with A prime B. Okay, so if for some reason you are in a closed system, of course, you don't add anything else, you are able to increase the amount of AB. It can only occur if AB takes that A of AB prime and this B of A prime B. So if this increases, these two other corners, they decrease. So these are antagonists. This is okay, that's sort of what you expect. But now let's look at the diagonals. That's much more interesting. If you look at the green diagonals, AB does not share a component with A prime B prime. So they are not in competition. So if AB increases, it liberates this A prime and this B prime, which can make A prime B prime, which means that the corners are linked by the diagonals. The constituents linked by the diagonals are agonistic. That means if AB increases, A prime B prime must increase. That's very interesting. That means in a complex, this is of course the simplest network, but that means in complex networks, there are relationships which make that if one changes, others will decrease. If one increases, one constituent increases, number of other constituents in the system will decrease, but some will increase at the same time. And so this, I like to call this agonist amplification, which is interesting. You can translate it in a more provocative way to say that the fittest drives also amplification of the unfittest. But of course, that means the fittest for a given type of property drives the amplification of the unfittest for the same type of property. And these are adaptive chemical networks. Let me just illustrate that in a simple way. If you take these constituents which are able to complex metals, AB prime, A prime B, and A prime B prime. If you add a metal to these four constituents, you will have a complexation with the constituent which is the best complexing agent, which is AB. You see here. Since there is an NH here, you can also ionize it. It's even more stable. That's a sort of secondary type of effect. So what happens if you add a metal? You enforce the statistical distribution, which was initially the case, then is enforced in a new distribution, gives a new distribution where you have only the fittest and the unfittest. And this can be done, for instance, using, in this case, a zinc, which we have done, and which you can see that indeed at the end of it, you have only two and not four anymore, because the midline has driven the amplification of the best ligand, which has led as a consequence to the amplification of worst ligand. So the fittest for midline binding drives amplification of the unfittest. And this can be represented by this scheme, this square scheme, where addition of a middle leads to the amplification of the one which binds best the middle cation, and it also amplifies the other one. This is an adaptation, and then again, this is very. We'll see that later again, because I think it's a very important factor in this complex exchanging dynamic networks, that agonist amplification, where the fittest for a given property is the unfittest, drives also the amplification of the unfittest for that property. Now, let's have a look. Wait a minute. I need a little bit more time. I hope that's all right. We have also looked at a system where we don't use now linear dynamic polymers, but these columnar ones. What is well known in biophysics is that guanine residues, guanine is one guanosine. This guanosine, a derivative of guanosine, one of the components of nucleic acids. But here there's just the unit itself. It is well known for many years that this can form a quadruplex. That means a G4 quartet, guanine quartet, where 4 guanines are linked by non-Watson-Crick. That is not a Watson-Crick assembly like in DNA. It is a Hook-Stain assembly where you can form a quartet of 4 of these guanines. And they are stabilized also by potassium ions, for instance. But the important thing is they use this non-Watson-Crick type of hydrogen bonding through this so-called Hook-Stain type of hydrogen bonding. So what happens then? What happens is that these discs which are formed here, this is coming back to what I showed you right at the beginning, where you form a disc of 4 of a quadruplex. At the beginning, I showed you one which is a trimer and one which is a hexamer, the rosettes. We come back to the rosettes in a moment. So this is now a quadruplex, a quartet, not a trimer, but a tetramer. And they form a column by piling up these discs which are formed of these quartet, guanine quartets. And they form indeed by transmission electron microscopy. This was also an Indian co-worker, Nampali Srivasachari, and this was the work which I now will show is the one done by him. So it forms this quartet. So this is quite interesting because, first of all, you make as I have said earlier on, the sector, which is this one, makes the quadruplex here, the quartet here, and these quartets can then pile up in 2 steps of supramolecular organization. Supramolecular hydrogen bonding here, and here supramolecular stacking of the discs. Now, suppose you do the following. You take now a system where you have only 3 components. One is a guanine derivative, this hydroxide here. The other one is a derivative of serine, another amino acid. This is an amino acid. That's a component of nucleic acids. You treat it now with pyridoxal phosphate, which is a well-known cofactor of transaminase. And so, what do you get? Very interesting. You would say, all right, if you put enough of it, then you will get, you should get a statistical distribution. There's no reason why this guy here reacts with this one and not with this one, or the reverse. So you should get statistics 50% of each. But that's not at all what you get. If you analyze, you find that you have 87% of this one and only 13% of this one. Why? That is very strange. Because, in fact, this one can form a quartet. It can form these discs, it can form this gel, which is a more organized state of matter than just a solution. So we see already here something coming out. Organization has a very important chemical effect also, not just a physical, but a chemical effect. And this is just representing it. You start with the initial ones. This one, the black one, is the pyridoxal phosphate. The red and the blue is these ones. And you end up with a gel, which is formed by this one and which drives selectively the formation of the gel. The fact that the gel can form drives the formation of the gel. That is sort of, we come back to that in a moment. Now, suppose we take now the system again with the four constituents as I indicated earlier. You take here A prime, B prime, two hydroxides, NH2 here and NH2 here, two aldehydes, pyridoxal phosphate and sulfobenzaldehyde, sulfonated benzaldehyde. You mix that. What do you get? You get a gel. Then you can analyze that gel by NMR. Of course, there are four possibilities. One of them forms the gel. This one you will not see by NMR because the bands are too broad. The other ones are forming something which is in a solution, so you can see them by NMR and analyze. What you find out is that the solution which surrounds the gel, so to say, has A prime, B prime, and A B. And you can see that A B prime is a high amount, and AB is the one you don't see, but you can calculate it by difference, of course. The ABs, they don't float away, they stay there. And so if you analyze that, you find that AB, the gel-forming unit, which you cannot see by NMR, is about 40%. Why do we know that? Because A B prime is 40%. This we can measure. And since they are agonists, they must be the same percentage. The A prime and A Bs are only 10%. So what is that? What does that mean? The agonists, of course, you find them, and then the antagonists are the ones which go down. So the agonists go up in percentage. And what is the conclusion? You amplify the constituent AB, which leads to gel formation. And of course, we together with its agonist, A B prime. This is what you get. So the gelation, you can calculate the driving force. The gelation driving force is the difference between 80% and 20%. It's about 1 kilocalorie. And so the fact that the system can self-organize. In other words, that among the four constituents, there is one of them which can self-organize. That one will dominate the system and say, I want to form, and you have to give me your pieces. And that's what happens. The selection is driven. You then select specifically AB, you amplify AB, because that's the one which gives organized matter, a gel, compared to unorganized matter, the rest, which are solutions. So this is already quite clear, and I don't want to go into this. This is just doing, again, the representation, unorganized in solution, organized in gel, organized state, and the self-organization drives the system. As you can see here, you get then the system AB and A prime, B prime amplified, and the other ones are then decrease in percentage. It's an adaptation to self-organization. Well, that is the important thing. Again, the fittest drives the unfittest. And this is something I come back, so I don't discuss it now here. But again, I can say that the fact that a system can lead to a gel drives the formation of a common component, which is among the constituents which can form. And so the possibility of the formation of a gel drives the selection of the one which gives the gel. I come back to that because I think this is very important, and it's also something to do with prebiotic evolution of matter. In general terms, I will come back to that in a moment. I'm almost finished. It means that the fact that matter can organize in a given exchanging system will lead to the selection of those things which can lead to organization. That can be very important in the origin of life. So let me now come back to the end where we go now to what you saw a moment ago is just the system which is based on the formation of quartets, which was done by Srinivasachari Nampali. And now my Chinese co-worker, my Indian co-worker, and now comes a Chinese co-worker. There were only people from Asia which did this work. I'm quite happy about that. So this is the Knoevenagel exchange reaction. And this is the question the system which can lead to this gel. Sorry, the exchanging in the solution. The Knoevenagel component reacting with the imine to lead to this intermediate acetidine, and then exchanging the red and the blue components. So you mix those together. You mix the Knoevenagel with the blue residue, with the imine, with the red residue, and you look at what happens. First of all, they can, as I told right at the beginning, form this famous rosette, which was studied by David Reinhardt, mostly, not only, but he did very, very nice work. Okay, this rosette. Now, this rosette is a molecular disk. So this molecular disk can form, I showed already at the beginning, can form a columnar supramolecular polymer. So the hexameric supramolecular macrocycle can form this columnar supramolecular gel. And it's a columnar supramolecular polymer. So what you expect is, of course, from what I told you already with the system with guanines, is that this gel will drive the selection, will drive the system to form the gel. So there's a two-step self-organization. First, you make the rosettes, and from the rosettes to make the supramolecular polymer. So this is a little bit complicated because we then selected constituents which would be able, one of them should be able to form a gel. Of course, we studied the whole system separately first, making each of the constituents, so that the KN1, so making these constituents KN1, A3, KN3, and A1. One thing which is important here is that there is one of them which we choose with this residue, which has 3 C12H25 chains. That means 36 CH2 groups of carbon hydrogen groups, hydrocarbon groups, and this must lead to a gel. This has so many, so 3 long chains, and this then should be the one forming a gel. And we had shown separately by doing the experiment that indeed it forms a gel. So what happens then? If you now look at NMR relaxation times, you want to know what is the, let's say, the organization of what you get of your sample. When you mix all this, you get a gel. How can you appreciate quantitatively the mobility, let's say the organization? The organization is linked to the mobility of the components of this gel. And so when you look at the NMR, the line width of the signals is broader if there is less motion. Less motion means more organization. So if all you have to do, if you take an NMR spectrum and you change the temperature, as long as you have a gel, the bands are very broad. And when you read the temperature when the gel goes to the solver, it melts, the gel melts, then the bands become much sharper. And so you can appreciate, you can you have an idea from the NMR relaxation times of the mobility of the molecular mobility in your sample, going from a gel where one of the components, this one, the green one, forms a gel, and the other ones are in this not form a gel. And when you go to the solution, then they become 25% each. So I give you just in a very simplified way the result in the solution. All 4, these 4 here, you see here on top, these 4 are in about 25% statistical distribution solution. Now, all you do is to change a little bit the temperature. And suddenly, yeah, suddenly it is a melting, but it's not so sudden in this case. You get in the gel a totally different distribution where you have 80% of the two, which about 50% or 45% of the one, the green one, which forms the gel, 45%, 44 of the one which is the agonist of the green, and the antagonists, they are only 6%. In other words, a very simple physical modification, which is a modification in temperature, leads to total recombination and redistribution of the constituents. And this is, I think, a very important property of matter. Property of matter, which I want to then just elaborate a little bit on it. Let's say just that here we have just 4 constituents. Of course, a very complex system with many more. These specific properties may disappear. The multiplicity may destroy the observation of this type of phenomena. So the next step in the evolution of complex matter is that you need a confinement, a compartmentalization, so as to avoid the washing out of the effect of the order generation by the combinatorial, the explosion you get as when you increase the number of components, when you increase the library size. But so let me just show you what we do then. You have to do a compartmentalization, which is also interesting because it means that is something which looks like the formation of cells. Again, compartments, cells. And we have results now which indicate that when you have a solution with 25% of each constituent, if one of them can lead to micelle formation, the micelle will drive the system to lead to the amplification of the one which forms the gel. So this is already a sort of a step further. But I would now just to conclude by insisting on what I find the most important is the following. Self-amplification organization. In other words, molecular matter has this property of self-amplifying the constituents of this matter, which are more organized than the ones you start with. Self-organization driven amplification of these entities which reinforce organization. At the beginning, we have this, okay, 25% of each. This is what you have. Then we cool down and we reach the region where the gels can form. And you suddenly have this strong amplification of the one which forms the gel and the one which is its agonist, like this. And then this is an increase in order. Increase in order meaning from a solution to a jelly, a gel. And if you heat, you go back. So what does it mean? Here, maybe I'm a little provocative, perhaps. If a system can reach a more organized state, it will go there. In other words, if order can be, order will be. That is not against the second principle of the second law of thermodynamics. It's because it's not delta S, it's not just entropy, it's delta G, free energy, which is important. And this means also that there is a drive to organization. Is it a cosmic imperative in our universe? I'm convinced of it, yeah, because of thermodynamics. It's just thermodynamics. No new, in that respect, it's just thermodynamics. And thermodynamics drives not just our world, our universe. It's an intrinsic property in our universe of visible matter. I repeat by the simple statement that if organization can happen, it will happen. And if we translate it into a more provocative way, if order can be, order will be. The system, if it can, of course, generate all these entities, like in a dynamic system, as I showed you, then the system will automatically go where order exists. Okay? I hope I've been clear enough. Thank you very much for listening. I don't hear you. You are switched off. Can you please put it on? I don't hear you.
Yes, can you hear me, Jean-Marie?
Oh, now I hear you. Yeah.
So thank you very much for this thrilling lecture, very, very inspirational. To close the session, I will give the mic to Professor Nitin Seth, who is the director of CEFIPRA, and he wants to thank you personally for this great lecture.
Thank you very much.
Thank you, Professor.
Thanks for the invitation also.
Thank you very much, Professor. On behalf of CEFIPRA, I would like to extend our heartfelt thanks and gratitude for your insightful and thought-provoking lecture on dynamic materials towards the functional and adaptive materials. We are really grateful for your virtual presence. We sincerely regret hosting you in person, and we would love to welcome you in India. So I'd like to invite you also to visit India. Thank you once again for your invaluable contributions. We are eagerly waiting for your personal confirmations and personal lectures, which I will talk to you. Thank you very much. Merci beaucoup for your lectures. Thank you.
Thank you. Thank you. I would, next time I will come to India, I will come. You are, where are you located right now?
We are in Delhi. We are in Delhi.
Yeah, in Chennai?
In Delhi only. Delhi. North part.
Oh, in Delhi.
Delhi, North.
I see.
And
okay.
I would like to express on behalf of Ministry of Europe and Foreign Affairs, Government of France, and Department of Science and Technology, sincere thanks to you for your agreeing to accept this assignment of virtual lecturing all the entire court. Thank you very much.
Thank you very much for listening. And I am sorry I went a little bit over time, but now we have a good dinner, I hope. Okay.
Yeah, it's a Sunday, so we are very much thankful to you to sparing time on weekends. Thank you.
Bye, everybody.
Bye.
Okay.
Mercy.
Bye. Thank you.